already had a chance of looking at the notes, but let us go through them together, and let us simply repeat what you should know as chemists or physicists about thermodynamics. Now, another thing is, I don't really know how fast we go. And it changes from year to year. And it may be, so we will go through the thermodynamics. I will put a short overview, a short plan of the course on the net. Maybe today, maybe tomorrow, probably tomorrow, because I have another meeting after this, 4 hours, maybe with a break we spend together. And there will be also the literature, but I think I will put a short overview of the whole course there with the minimal requirements, which you will have to reach at the end, and with the books. So essentially, you can read whatever you want, but they are simple books and they are complicated books. Take simple, take Thin Doi, Dejean is a bit more complicated, or Grossberg and Khokhlov. Rubinstein is very good, but very thick. Tomorrow, probably I will give you the references. Today we have anyhow only the, so to say, this repetition and, okay, let's have a look. So the largest part, in the best case, the 2/3 of the course will be thermodynamical properties, which are essentially the statical properties of polymer molecules and polymer materials. And then I would like to go to dynamics, to viscoelasticity, to viscosity, and so on. But some years I have enough time, some years I don't have time at all to talk about this. But anyhow, you will get some basics, at least of the thermodynamics of materials. And this is what I am speaking about here. Now, I think Mr. Kirstein, who is the coordinator of our course in Humboldt, has already put all the dates. You know where our examination is? Do you know? It's a question to the audience. I have forgotten.
No.
No. He will tell you. I think it's still during the teaching term, during to some regulations, because we have I think it's somewhere in the end of February. So we only have 2 months, but essentially less than 2 months. And therefore, I don't know where we stop, but I know where we start. Now, now let's go a little bit further. What we will be doing is a kind of statistical thermodynamics of polymer molecules and polymer materials. So the polymer molecules by themselves are large enough to consider them as complex systems to apply thermodynamics to a single molecule. It's something different from simple molecules, small molecules, where you have to describe them essentially on the atomistic level. In the polymeric molecules or materials, there is enough scales between the single atom and the molecule so that you can consider a molecule alone as a polymeric, as a thermodynamical system, and the polymer material anyhow, as any material. Now, although you definitely have had your thermodynamics, let me shortly go through this repetition. So who didn't have any thermodynamics in your study? Is there anybody? Let me open the chat. Is there anybody who didn't have thermodynamics? Okay. I don't see any, so this is nice. I'm happy with this. So let's go. Thermodynamics by itself is a phenomenological theory, and the word phenomenological means that it's based essentially on generalization of experimental observations. In physics, they say there are two kinds of theories. There is phenomenology, and there are microscopic theories when you know what is behind it. And we will use the both, and there is a connection. So on the microscopic levels, we have single atoms, we have single molecules, so atomic bonds, and essentially the atomic description, the atomistic description is a realm of chemistry. Everything at this scale depends on what kind of atoms, what kind of constituents you have in your system. And the higher you get, the larger you get in scale, the more and more the behaviors typical for complexity appears. And there are only few properties of the atomistic structure which are transported upwards to macroscopic variables. Now, the thermodynamical description is based on using the coarse-grained description, on using a very few collective variables which characterize a thermodynamical system as a whole. And you know these variables, they are, so to say, they are listed, they are patented variables, yes? And these are, of course, the thermodynamical potentials you have heard about, which are internal energy, free energy, enthalpy, whatever Gibbs potential. And there are the state variables other than potentials, like the number of molecules or number of moles and pressure and temperature and whatever. So you have very few variables by which you describe the system. And these variables give you a kind, essentially they define the kind of description we call the thermodynamical level. This is not that you cannot go to the microscopic variables. This is not that you cannot measure a velocity of a single molecule. Now you can, and you can even see a single molecule, you can follow a single molecule. This is simply that for understanding the properties of a material, you don't want to. You don't need a description which is too detailed because you get lost in details. And the roughest possible kind of description is indeed given by thermodynamics. Now, the phenomenological formulation of thermodynamics is based on the laws of thermodynamics, which are four. These are the physical laws. There is a full mathematical axiomatics of thermodynamics, which chemists probably have never heard about. And the total number of mathematical axioms is huge. For example, what we physicists call the second law, I know it by chance, are 26 mathematical axioms, if you want to put it mathematically, but we don't need it. Now, and in between, the translation between the molecular structure and the thermodynamical description is given by statistical physics. So this is the intermediate level here, where my face is between my two hands. And we will only scratch a little bit this kind of description. I will constantly use it, but I will use the simplest possible variant. And therefore, we will learn how it works, but we will not learn why it works. So I'm not giving, unfortunately, I love to give it. It's a full one semester course, which means it's not, in the simplest variant is 32 lectures I'm giving in statistical physics. And then one can understand more or less why it works. But we can understand on a very simple level how it works. Now, let us start from repetition of thermodynamics. Do you know and remember the 4 laws? Who remembers the 4 laws?
I can remember them. We have the zero law when we approach or try to understand the equilibrium, the thermodynamical equilibrium. The first law is the law of conservation of energy, where in a system we can transfer energy, but out in or out of the system, but the energy is conserved. So we have to keep this balance between the output and the outlet of energies of the system. And the second law is related to entropy, and we relate the degree of entropy. Normally a system decreases the degree of entropy, increases the degree of entropy. And the third law, we studied some parameters by considering the zero, the absolute zero, temperature. I mean 0 Kelvin.
Okay, wonderful. So
Thank you.
you know it. Thank you so much. And
You're welcome. My pleasure.
so let me repeat it once again. So we have this zeroth law. There are on the total 4 of them, and somehow people first didn't formulate the zeros, and therefore they decided to put it before the first and not after the third, on historical reason, because Nernst, who formulated the third one, said that there was a joke that the first law had 3 fathers. The second one, 2, the Clausius and Helmholtz. The third one, 1, Nernst, and therefore they cannot be the fourth. So when one needed an additional axiom, it was clear that it was needed, but the full axiomatization of thermodynamics happened only in the beginning of 20th century, and the first law is the beginning, the first third of the 19th century. So when they put the full axiomatics, they decided to put the law of equilibrium as the zeroth one. So if you have a system, then if the system is led to itself, this one will reach a state, a macro state, which will not change anymore in course of the time. And this state we call the thermodynamical equilibrium of a single system. So we consider an isolated system, and we state by observation that all the macroscopic motions, all the transport processes, everything in the system, which we can observe on the macroscopic level, in course of the time comes to a halt, and the system doesn't change anymore. And we call this state equilibrium. Now, if you have a composite, now let me draw something on my blackboard. If you want, I can stop the script, but essentially you can also enlarge my face if you want. Now, do I have to stop the script? or you can see the blackboard and look only on it. It depends on your preferences.
It will be great if you close the script.
Okay.
Yeah, please stop it
for a second. And now I will also look at myself, because then I will see what I'm writing on the screen. So here there is a blackboard. So let us imagine that I have a system. This is my system. It's isolated, which means it does not, can you see it? It's green. It does not communicate with the environment, with the surrounding. And now let me imagine that this system consists of two subsystems. So there are two pieces of metal which I brought together. At the beginning, one was hotter than the other, for example, and at the end, they will come to the same temperature. This is then the equilibrium. This will be T1, this will be T2. And essentially, an important property of the equilibrium is that, so now I have the heat exchange between them, and both are at the same temperature. Now maybe this is permeable and this membrane, and there will be exchange of molecules, and then at the end of the day, the mechanical pressures and the chemical potentials in both parts of the system will be the same. But temperature, the equilibration of the temperature is the most important property of establishing the equilibrium. Essentially, I can say that if the temperatures of subsystems, these two, the two subsystems are the same, the system as a whole may be at equilibrium, in an equilibrium state. If the temperatures are different, it is definitely not in the equilibrium state. Now, another important property of equilibrium is that if I now separate the two parts of a system which have been in equilibrium and then bring them again together, so I bring them together again, nothing will change, and the whole system will be in equilibrium again. And the third important property of equilibrium is the transitivity of equilibrium. If there is a third system which is in equilibrium with this one, so I put it in contact with this system, nothing changes. And then I take it away and put it in a contact with another subsystem. And I see that nothing changes. Then the two systems are in equilibrium with each other. So if the two are in equilibrium with the third one, these two are also in equilibrium with each other. And we use this property for measurement of the temperature. This you can consider the thermometer. So I bring a thermometer in contact with a system. It acquires the temperature of the system and shows me the temperature of the system. And then I bring it in equilibrium with another system, and I see whether the temperatures were the same or the temperatures were different. So these are the things there. And this is essentially what one has to know at the beginning about the zeroth law. Now, the classical thermodynamics is essentially the thermodynamics of equilibria. The systems are assumed to be more or less homogeneous, or homogeneous in larger parts. So I can speak about the, at least about the small parts of the systems as being in a state of equilibrium, or maybe close enough to equilibrium, to use the formalism of thermodynamics. And I also assume all the processes to go slowly enough that this condition of quasi-equilibrium is fulfilled at all times. And then I can use the standard thermodynamics. If it is no more the case, I have to use a more complicated formalism of non-equilibrium thermodynamics, or I must go to the full statistical description within the theory we called kinetics. So if we consider the processes which are fast enough, which lay outside of the classical equilibrium or close to equilibrium thermodynamical description, I need a different approach. I need a different theory. Okay, now this we know, and let's go back to the screen. We have now this zeroth law and its consequences. Now we have the first law, and again I will simply repeat what you have to know. And now we consider a system, might be isolated or not. It's important that essentially I can always separate the system from its surroundings, and the interaction with surroundings is not extremely strong. So I can speak about the system alone, and all the exchanges are slow enough. And then I can say I know from physics that each system of interacting particles at each instant of time does possess the energy. And I call the full energy, the normal energy of the system, the physical energy, the sum of kinetic and potential energies, or if you want, if you learn some quantum mechanics, the quantum mechanical mean of the Hamiltonian of the system alone, I call this the internal energy of the system. So this guy has an energy. And this guy can exchange energy with the surroundings. For example, if these two guys were at different temperatures and I brought them together, there is an exchange of energy. And the energy will flow from a hotter system to a cooler system. This we know then from the second law, but imagine we know it, so there is a flow of energy. This flow of energy is not accompanied by the macroscopic mechanical work because the form, the shape of the system doesn't change. Nothing moves. In order to have mechanical work, I have to have motion, because work is an integral of force times displacement. If there is no displacement, there is no work. But there is an exchange of energy in form of heat. And then the first law is indeed only the law of energy conservation, and it states that the change here written as a differential doesn't matter. The change of the internal energy is due to performing work, mechanical work on your system, and is due to heat exchange between the system and the surroundings. And in the heat, there are all other interactions which do not change the macroscopic form of your system. Now, the energy is a property of a system alone, while the work and the heat are the properties of a process, of what I am doing with my system. And therefore, I have here different, so to say, notations, different signs. Here I have D as a differential, and here I have it's called total differentials. And here I have differential work and differential heat, which simply means I am free to choose a process or to choose a protocol of a given process. A protocol is a time dependence of external influences. And the work and the heat depend on the protocol of what I am doing to my system. It's funny how one discovered this law, but I don't think we have to talk about this. Now we have the second law, which is essentially a genuine law of thermodynamics, because we have here a new notion, and this is a new notion of entropy and its conjugated variable, the temperature, which are interesting. Why are they interesting? The internal energy, or the energy by itself, is a mechanical quantity. If you haven't learned quantum mechanics, doesn't matter. Chemists essentially have to have at least rudimentary, and physicists anyhow, rudimentary knowledge of quantum mechanics. The energy is a mechanical quantity. If you calculate the work, it's a mechanical quantity. Okay, heat is not a mechanical quantity, but on the microscopic level, it's simply a kind of energy transfer. Everything you look at here is mechanical. You can express everything via coordinates and momenta of the particles of the microscopic constituents of your system. There is nothing genuinely thermodynamical here. And in the second law, we meet a variable which does not have a mechanical analog. You can calculate entropy from the properties of the system, but it is not a mechanical variable. It is not a mean, quantum mechanically speaking, of anything, of any mechanical variable. You cannot immediately obtain it via coordinates and momenta of particles. It has to do with something else. We will talk about what does it have to do with, but it's a non-mechanical quantity. It has many incarnations, I would say, in thermodynamics. And what is the most important is that it governs the direction of thermodynamical processes. I can took in my mouth some words which we probably never heard about, but I will take them in my mouth, and I will say that it is a universal Lyapunov function of a thermodynamical system, of a complex system. In order to be able to quantify mathematically what is equilibrium, and the theory of equilibrium appeared essentially, the mathematical theory of equilibrium appeared essentially at the beginning of the 20th century, you have to introduce some property of the system. You typically say that first everything changes and then nothing changes, yes? When you say that the system is approaching equilibrium. But essentially, it can be that you have chosen a variable. For example, in an isolated system, you are looking at the energy, or maybe at mean velocity of the particles, or maybe it didn't change from the very beginning. If you don't perform work or exchange heat, the energy is also constant, whether your system is in equilibrium or not. So you need a universal function, sorry, a universal function of the state variables of your system, using which you can say that the system is approaching equilibrium and that the system has reached its equilibrium. And when mathematicians were creating the universal theory of equilibria, they came, and there was a Russian guy, Alexei Lyapunov. They came to the idea that there must exist a function of the properties of the system. In our case, this will be a function of the state variables of our system, such lambda of t, that if I'm looking at this function as a function of the time, this function must be monotonic. You say it's approaching equilibrium, and this means if it's always approaching equilibrium, the function must be monotonic, which means it's either decays monotonically or it grows monotonically. It cannot oscillate. Because I'm always approaching equilibrium. It doesn't mean that other parameters do not oscillate. Imagine you have a vessel with the ideal gas, and you have here a piston which is heavy. So you put the piston there, and you know that at the end there will be an equilibrium. This you know. But the piston, essentially, when you put it here, at the beginning, it's like a mass on a spring. It will oscillate. Yes? So the volume is not a Lyapunov function. At the end, the volume will not change, but at the beginning, it's oscillating. So you need something which does not oscillate. And so the function is monotonic, and when time grows, it reaches the limit. The classical mathematical definition is that it's monotonically decaying, which means that the lambda over dt is smaller or equal to 0, and it's bounded from below, and then it has a limit. And this is the Lyapunov function. And if the system has an equilibrium, it has to have a Lyapunov function. And what is interesting is that any thermodynamical system does have a Lyapunov function, and this is minus entropy, because entropy is growing. And in equilibrium, it reaches its maximum. Now let's go. Thermodynamics was earlier there than the classical theory of the mathematical theory of equilibrium. So I have a function which is monotonic, so all changes are positive, and which is bounded from above, which means it reaches its maximum when the system reaches the equilibrium. It was postulated, the existence of such function was postulated, and this growth of entropy, together with some other properties, I'm not giving now a lecture on thermodynamics, otherwise I will give several, so to say, lectures there, but let's imagine you know, or you still remember something of thermodynamics. So I have this property plus some other properties like additivity and so on, and they are enough to uniquely define the entropy. And this growth of entropy, together with statement of its extensivity, we will go there a little bit later, is enough to define this as a thermodynamical theory. Now, if the system is not isolated and there is some heat transport, then the transported heat is always larger or equal than the change in entropy divided by the temperature. And if the system is at each state of your process arbitrarily close to the equilibrium, you have here the equality. The heat, the transported heat, is the change of entropy divided by temperature. The temperature is changing very slowly, so at each time you have a well-defined temperature. You can then say that Q, this is wrong. Q is T ds, so which means that this is wrong. dq is larger than t times ds. I will correct it in the script and put it then correct. So it's ds larger than dq divided by t. So dq has to be here and ds has to be here. Doesn't matter. I will correct it. Now I have this most important thermodynamical variable, and it's very interesting how it appears. All the conceptual difficulties of the transition between microscopic dynamics and thermodynamics are essentially here. And they are due to the fact that all microscopic dynamics are time reversible. And it's entropy which governs essentially the direction of time. When entropy grows, I know that the time is going on as it should. And it's very hard to get a time-directed theory from a time-reversible one. The problem is essentially philosophically not fully solved. We know more or less how it happens and why it happens and what do we see. Why do we see it in complex systems? Why do we not see it in the simple systems due to returns and so on and so forth? But this is indeed a genuinely thermodynamical thing here, which does not exist in mechanics. Now there is a third law which we will not need, and this is that the entropy vanishes at zero temperature. Essentially, the entropy and all its derivatives with respect of all other thermodynamical variables do vanish at zero temperature. And again, this was formulated as a consequence of experimental observations. It is a deep law, and it's a law which does not exist in classical physics. It's a pure quantum mechanical statement, and it is, for physicists, intimately connected to the fact that the ground state of quantum mechanical systems is not degenerated. There exists only one ground state. Now, an important thing which we will continuously use in thermodynamics, in equilibrium thermodynamics, is the fact that thermodynamical variables do come in two classes. There are thermodynamical variables which are the same throughout the whole system. If I come back to my blackboard, you already remember my figure here, when now I consider here a mental, so to say, now I consider a mental border inside of the system. The system is considered as consisting of two subsystems. And I know that the temperature here is the same as temperature here. T1 is equal to T2. I know that in mechanical equilibrium, P1 is equal to P2. I know that the chemical potential, mu1, is equal to mu2. These thermodynamical variables, which are the same within the whole system or between different parts or subsystems of a single thermodynamical system, these are the intensive variables. If I look at the number of particles, then the number of particles in the whole system, n, is n1 plus n2. If I look at the energy, U, This is U1 plus U2. If I look at the entropy, then it is S1 plus S2. So here I have the variables which are additive. To get an energy of a system which is double so large, the energy of a system which is twice as large as the initial one will be twice as large. The number of particles of a system at equilibrium, which is twice as large as my initial one, will be twice as large, and so on and so forth. This property that within thermodynamics I have only these two classes of thermodynamical variables is very important because it allows for many things. Those who have learned maybe remember Gibbs-Duhem relation, whose differential form and the possibility to introduce the Gibbs potential essentially is based on the extensivity of energetic variables and so on and so forth. So it's a very important classification which breaks down when you go away from equilibrium. Now, so we have here this, our internal energy as a function of thermodynamical parameters, and we have the work and we have the heat. Let's look at the work first, and the mechanical work is simply F dx. This you know from mechanics. Now, what is F? First, F is either the force you exert on the system or the force which the system exerts on you. So here I have this is one of the masks I have in my office, and this is a spring or a piece of rubber. Yes? If I act on this piece of rubber, pulling it, the force is acting in this direction. It's positive. The displacement is positive if we imagine that the x-axis is showing in the direction of my finger. My grandmother taught me that it's not nice to show on something with a finger, but I'm too lazy to draw the axis. So now this is a positive work. This is my work. And the energy of the piece of rubber is increased, the internal energy. I can use it then because it can produce work by itself if it's pulled. For example, I can use it for shooting a piece of paper somewhere. This is my force, the force I apply to the system. If I would ask what is the work expressed via the tangent force, and this is now a force which this piece of rubber exerts on my hand. This will come with minus here, if you see my hand on the PDF here. This will come with minus. Keep this in mind. Plus and minus are important, and sometimes one has to think what kind of a force are you considering. This is your force or the system's force on you. But this is not complicated at all. Now, we will be in many cases interested in pressures, and pressure is essentially simply a force per unit area. In my example, which I already removed here, with a piston, so I have here a cylinder, a vessel, I have here, it's with gas, for example, I have here a piston, and here I have gas, and the force acting on a piston is F minus P times, or Fp times S. And it's going here upwards. if I want to increase the energy, if I perform the work, I have to act with a force which is minus F on this. The pressure acts up in this configuration. I have to act down. So dA is minus P dV. It's easy to obtain because dA is F. dx is F is minus PS dx, and this is dV. So this is then the corresponding work differential in this case. And now I can put down the change of the internal energy for a quasi-static process in terms of the work differentials. Now, if I remove or add molecules, I also change the energy. The energy added per added molecule is called the chemical potential of the system. And there might be other possibilities to act on my system. I can switch on the electric field or switch it off. I can switch on the magnetic field or switch it off. I can do something else. And then I can put down this du, this infinitesimally small change of the internal energy as a sum, as a differential form. Minus PdV, this is the pressure in my system, times the change in the volume, plus chemical potential in my system for a corresponding sort of molecules, times the change of the number of molecules of the corresponding time. If I have a mixture, I have different chemical potentials. I might have different chemical potentials for different constituents of this mixture. And then at the end, I have dq, and dq is put in this form for quasi-static process, and this is TdS. This form is called the Gibbs fundamental equation, and this is essentially the main mathematical equation of classical equilibrium thermodynamics. Now look at the structure. And the structure of this differential form shows me what are the natural variables of the internal energy. And the natural variables of the functions are such which comes in its differential with this d sign, with the changes. So the internal energy is a function of volume, number of particles, whatever, entropy. An important property of the internal energy as a thermodynamical potential is that its all natural variables are extensive. Never forget it. Now, what else does it mean? Imagine you have just a general function of several variables. F, let's say, of x and y. I will put here two variables. Now, let me put the computer normal to the blackboard. Now I have this generic function, let's look at change of this function. The f is, I change a little bit these variables, and it will be the derivative, the f over the x plus the f over dy, this is a Taylor expansion, plus the second derivatives and so on. And I first neglect them, saying that the changes are small. And then I see that what precedes the changes of variables, and these are the natural variables. The natural variables of a function is what is written as a list in the definition of the function. Yes? The quantities preceding these d symbols in the change of the functions are the partial derivatives of this function with respect to its variables, which I now call the natural variables. And this means that the pressure is the derivative of the internal energy with respect to the volume, with minus in front. The chemical potential is the derivative of internal energy with respect to the number of particles, and temperature is the derivative of the internal energy with respect to the entropy. Now, the internal energy is not the best thermodynamical potential to work with. Of course, it's very nice if I can keep the entropy constant, which means I am working adiabatically or isentropically. But typically, I cannot, so I can prevent S from changing, but I cannot control S. Since it's not a mechanical variable or a non-mechanical variable, there is no machine which measures entropy immediately. So there is no entropimeter. I have a thermometer, I can measure the volume, I can measure the number of moles or control it, but I cannot measure entropy. But I can easily measure temperature. So for many applications, it's nicer to work with a thermodynamical potential which has temperature instead of entropy as its natural variable. Because you already have done in your life, at least in the lab, some experiments, and it's not only easy to control temperature, it's easy to change temperature. You are able to keep entropy constant, but you are not able to change entropy by exactly, I don't know how many joule per Kelvin, let's say by 1 joule per Kelvin. This is hard. And it's very easy to control and to control in a controllable manner the temperature. So I need a potential who has temperature as its natural variable. And this potential you also know, or you should know. And this is the free energy. And it's U minus T times S. Now, this is, in mathematics, this kind of transformation is called the Legendre transformation. It's a little bit more complicated that I will represent it here, but if you are safe in thermodynamics if you simply define this as U minus T times S. Essentially, a Legendre transformation is, I will not talk about this. Now, why do I know that this guy has temperature as its natural variable? Okay, this is easy to see. Now, let me have a look at F equal U minus T times S. Now I look at df. This is du minus d of t times s. This is a small change of t and s. Both t and s do change when I change the state of my system. I cannot say that I don't have to keep any of them constant. And what is this guy? This is t ds plus s dt in the lowest order. Is it clear why?
Yes.
It's clear to everybody.
Yes.
Yes.
Yes. Yes.
Wonderful. And now I put for this guy the fundamental equation. So df is minus p dv plus mu dn plus blah 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 plus t ds minus t ds minus s dt. This guy go away, and I have here a change of t. And this gives me the list of variables of f, which are v and t. So what I did, I changed one extensive variable in the list for an intensive one. And this potential, which depends, all potentials which have temperature in their list of natural variables are called free. So it's F is free energy. And then in principle, we will not do it, but you definitely learned about this in thermodynamics. I can make similar transformations with other variables. For example, I can exchange V as a natural variable for P by adding PV to U, and then I get another thermodynamical potential, which is called, how is it called? If I look at U, at H equal to U plus PV. What is this?
Enthalpy.
This is enthalpy. So the potentials depending on P, and enthalpy, its list of variables is P and S, and something else if you need more. All these P-dependent, where you don't have the dependence on the volume, are enthalpies. Then I can also do this with N, exchanging N for mu. And then I obtain what? I obtain the grand potential. Everything which depends on mu are grand. Then I can combine two. I can have free enthalpy. The only thing which does not exist is the free grand enthalpy, because it is zero by Gibbs-Duhem relation, but we will never need it. Okay. Now, from the properties of internal energy and entropy, it follows that all reasonable thermodynamical potentials at equilibrium reach their minimum. The free energy is the nicest potential if I can keep temperature constant, because then I have one term less. And at constant temperature, the free energy always reaches its minimum at equilibrium. And this I will use because we will typically work with isothermal system with the systems given with a given temperature. And then if I would like to know what state does the system acquire in equilibrium, what are the values of the state variables of this system in equilibrium, I will put down the free energy as a function of parameters and minimize it with respect of parameters. For example, if I would like to understand if I have a system which might come in two states, which state is indeed realized. This is a typical situation in solutions, not only in polymer solution, but also in polymer solutions, when you can have either a homogeneous solution or you can have the phase separation. This is what one continuously uses in, let's say, metallurgy. You have an alloy, and from this alloy you want to get the pure elements. This is how you get, I don't know, metals from the ores. And then at some values of parameters, of temperature, of pressure, of whatever, you have your system, and it might come in two different states, homogeneous or separated. What do I do in order to understand what state is indeed stable, what state is the true equilibrium? I calculate, for example, the free energies or the enthalpies or whatever, the free enthalpies, and then I say, look at these values of parameters. The homogeneous state has lower potential, so I have a homogeneous alloy, and at another values of parameter, it separates into, let's say, two components. This is what we will do with the polymer solutions. Continuously, we will draw the phase diagram, we will look at this phase separation. There are many interesting things around there. And this is how it works. So the thermodynamical potentials and equilibrium have the minimum, and the lower the minimum, the more stable is the corresponding structure of the system. Now, until now, we only considered these macroscopic properties, the description of our system within the thermodynamics. And even for gases or fluids, you need some input into thermodynamics. So thermodynamics is a great theory. It gives you the connections between different thermodynamical variables, but you need some input. And as input for fluid systems, for example, you have to put down two equations of state. And chemists know these equations of state. So do the physicists know how they are called? What are the equations of state? This is a question to the audience. Does anybody know how do I get the... So what are the inputs to thermodynamics? Silence. Okay. Have you ever heard about thermal equation of state? What is this? There are two, thermal and caloric. No. As input to thermodynamics, you need two things. And you know, most of them, so they're very nice equations of state. What is the equation of state for the ideal gas, for example? Do you know this? the thermal equation of state for ideal gas.
PV equals nRT, nkBT.
Like this, or RU if you want. Essentially, the thermal equation of state gives you P as a function of V, N, and whatever, and T.
Excuse me, Professor, the board is not actually visible.
Now it is actually visible.
Yeah.
You have P as a function of temperature, therefore it's thermal. It gives you it gives you, let's say, force, because P is a force. As a generalized force, doesn't matter. The word generalized now doesn't mean anything. P is a function of T. This is the thermal equation of state. And the second equation of state is U as a function of V and T. What is for ideal gas U as a function of N and T? Let's imagine you have a single atomic molecule. This is the same as the equation for CV. 3 of KB and T. And this is the caloric equation of state. If you know these two equations of state, then the thermodynamical machinery, again, I am sure that the chemists have learned a lot about this thermodynamical machinery. From the equation of state, you get everything which is necessary. If you have reactions, you have to have as many equation of states as you have the components, the reactants, the products, and so on and so forth. But if you have the equations of state, the rest is done by the machinery. Chemists maybe did not go deeply into the mathematics of thermodynamics, which is essentially it's essentially differential geometry. Thermodynamics is about the geometry of the state space of the system, but chemists do not need it in their everyday work because one can calculate everything one needs as a chemist with relatively simple, well-prescribed instruments. Now, the question is, how can one get the equations of state? And here, of course, people can get them experimentally. This one you get in measuring pressure, and this one you get by calorimetric experiments. So you can measure, for example, the heat necessary to change the temperature by 1 degree by different volumes, or if you want by different pressures. If you then you recalculate the equation of state from the enthalpy change or whatever you want. So you can get them experimental. This is very nice, and there are huge tables for important fluids and gases and materials, solids, whatever. But to understand theoretically where do they come from, you need a theory. You need a connection between this thermodynamical level of description and microscopy. And this connection is given by the statistical physics. And the very, very first result of the statistical physics is the Boltzmann formula here, which connects the entropy with the number of different ways by which the corresponding macro state can be realized. Now, a question. Did you have it in your course of thermodynamics or statistical thermodynamics or chemical thermodynamics?
For me, no.
Yeah.
No. Yes.
No.
No, yes. Okay. This is where we will start from. Now, it's the following. When I am, first, if you want, it's a postulate. But behind this postulate, there is a huge theory of statistical ensembles. And again, here, I will not be able to start building this statistical ensemble theory, which was essentially started by Gibbs. Boltzmann postulated it in order to be able to explain what do we see. If we have a macroscopic system, then very different configurations. Imagine you have an ideal gas in some vessel, and you have their molecules, and the same value of pressure and the same value of temperature in your vessel will correspond to very different possible positions of the molecules, momenta of the molecules, directions of motion of the molecules. So there are many ways to realize the corresponding result. And Boltzmann simply said that the entropy is maybe up to an additive constant. So maybe you can put here some S0, is proportional to the number of ways of different realizations of your microscopic system, which gives you the same values of macroscopic parameters. W is the number of configurations of microstates of your system, which gives you the given value, the observed values of macroscopic parameters. There are different approaches to explanation of this postulate. Let's assume it as a postulate, because I don't have time to go deep into statistical physics. There are different approaches to this postulate. One is to derive it from mechanics. And this is what Boltzmann tried in 1860, I don't remember, 3, I think, 62, 63. And another one due to James, and this is the 20th century, is the informational one. One says this is because the true mechanical systems and the classical system essentially don't want to behave like this. It's true to show. It's hard to show. In quantum mechanics, it's easier to work with, because W is simply the true number of quantum states. Of if you have a quantum system in a confined volume, its spectrum is discrete. The number of states can be counted, and this W is a number of quantum states within some intervals. I don't go into details now. You know, I will not need them, and otherwise I will have to, again, to give half a course in statistical physics, which I don't plan to do now. This is one way. And another way, this is what Jaynes advocated, was the following. He said, look, what I am essentially doing, I don't want to explain why. I want to predict how. So the question is, what is my best prediction about the properties of the corresponding macroscopic complex system given the information I have about this system? And it's an information theoretical approach. And from this approach, you also immediately, essentially in 3 lines, obtain this formula. But again, I'm not going to obtain it now. because before these 3 lines, I need an hour of explanation of what information is and how to predict something under lack of precise information. So I simply say it is like this, and this is where we start. Now I have a question to the audience, and the question is as follows. Do we make a break or we do not make a break here? Because I am talking for 1.5 hours and I can drink some coffee, we can make 15 minutes break or half an hour break and then rejoin, and I will finish the lecture and we will start our tutorial.
I would go for the break.
Sounds good to me as well.
Okay, now let me stop here. Yes, let me open the gallery to see your faces. Who is for a break? I'm for a break. Okay, let's make a break. I will even not close the session, but I will make some coffee for myself and go to the men's room, and then we rejoin when? Let's rejoin quarter past.
Okay.
Okay, so I leave computer here and we rejoin quarter past. I switch off on the coffee machine. Now I will switch off my microphone. that the fact that it does not really matter with what accuracy you perform your measurement, it's a remarkable problem. Now, it means that this W, the resolution, must be good enough, but it doesn't matter not for the absolute value of S, but for the dependence of S on other thermodynamical variables. It doesn't matter how accurately you resolve your system. Now, before I simply follow here this script, and before we consider the examples, let me say that we will mostly play with the models where the internal energy does not depend on the configuration. It's very typical, which means does not depend. It's very typical in polymer physics in models, in approximations. For example, if you have an absolutely flexible chain, or let's say a freely rotating chain, the internal energy does not depend on angles, which are essentially the relevant variables. And in classical physics, the kinetic energy, the mean kinetic energy, is anyhow the function of temperature only. You have kBT half per degree of freedom. So these kind of models, not real system, but models, correspond to an interesting U. It doesn't matter, then it doesn't mean that U is not there. There is internal energy, and it's a function of temperature. But all the interesting dependencies on other thermodynamical variables come via entropy. And it's very nice to consider here the free energy, and then you first calculate the entropy, and then you know the free energy. And it's not the whole entropy, it's part of the entropy, but entropy is defined up to, in classics, up to an additive constant anyhow. And now I wanted to consider an example. And my example will be, my first example, will be the ideal gas. And I will do this ideal gas. I will show the two-dimensional pictures, but you can do it also in 3D, and for polymers we will always do it in 3D. So now I switch off the script and show my blackboard on which I draw what I mean. So I will only consider the configurations, which means I only consider the positions of the particles, and I forget the kinetic energy. Again, I do not explain why I can do it. I cannot do it if I am interested in such things like specific heats, which depend only on kinetic energy for the ideal gas. But I am interested now only in the thermal equation of state. I am interested in pressure. And I will start from the following model. This is my vessel in which I have my ideal gas. And ideal gas is a model. It's not a real physical system, it's a model in which the molecules are the point particles. And there is no force between the molecules. And as you know, the point particles essentially, they are points. It's very improbable that they somehow hit each other. It's a little bit a contradictory model, because if the particles do not interact, they cannot equilibrate. But one can imagine that there are some external mechanisms of equilibration. I have a model. Now, how will I calculate the configurational part of the entropy, the part of the entropy which depends on the positions? Because in classics, and once again, for physicists have probably learned it, chemists, I don't know, the kinetic part of everything simply is independent on the configuration, and you can simply add it if necessary to the internal energy. And it is simply CV times T, and that's all. Doesn't matter. So what I do, I will consider my system. I will discretize my system and consider that there is some here lattice in 3 dimensions. This will be a kind of foam or froth of cells. And each cell, here quadratic, has the size A. And this is my discretization constant. This is a coarse gradient, because the real molecules live in continuous space. The coordinates are continuous. But I will count so that there is an infinite number of configurations, yes? But I will count the configurations by counting in which cells the molecules are sitting. And I will count the total number of such configurations which are available for my system. Now, in 3 dimensions, if the volume is V, the number of cells N is V divided by A cubed, because the volume of a single cell is A. And this is an arbitrary constant. I simply say I discretize my system according to this rule. A has to be taken small enough, and small enough here means that it simply has to be taken much smaller than the linear dimension of my system L, and L is cubic root of the volume V. And now for the ideal gas, for non-interacting particles, for no restrictions, the calculation of the number of states, of possible configurations, the configurational part of entropy, is extremely simple. And we will play with this a little bit in our tutorial. Because the molecules are independent. In an ideal gas, they don't feel that the other ones exist. So how many possibilities are there to place a molecule, now here a green molecule, within my system? For example, now I place a green molecule here. How many possibilities are there to place one green molecule in one of the cells of the system? Who can tell me? And I called it, in script, I call this M. So I have M cells. In probability theory, it's called an urn scheme. So you have an urn. This is a kind of vessel. So now I have here, just a second. Just a second. Here. I have 3 urns. I show you the 3 urns. Do you see my 3 urns?
Yes.
Yes. How many possibilities are there to place a single object in this system of 3 urns?
You have
3.
yes, you.
3.
3. How many possibilities are there to place 2 objects? 2. In this system of 3 urns?
2. Oh,
9.
no, together.
9.
Ah.
If the objects are independent and don't hinder each other's ability to sit everywhere, this is 9. For n objects, this will be 3 to the power of n. If I have m urns, like here, this will be m to the power of n. First, I have the distinguishable objects. In my example, it doesn't matter. We will discuss it a little bit later, but this is m to the power of n such possibilities. Now, if the objects are indistinguishable, it's slightly different. It's then written here, but we will consider this just a couple of minutes later. So now my W is m to the power of n. This W is the number of possibilities to place the objects, the molecules, and in my case it's m to the power of n. And now I take the Boltzmann formula and calculate the entropy. And the entropy is then Kb ln m to the power of n. Now ln m to the power of n is n times ln m. And then I use my expression for m, which was v divided by a cubed. And this is what I get. This is the configurational entropy of ideal gas of distinguishable molecules. But for me, it doesn't play a role now that they're distinguishable. It's not real physics. In physics, they are, if they are of the same sort, they're indistinguishable. But again, it doesn't matter. And now let's have a look what I get for the free energy. The kinetic part decouples, so the system is athermic because I don't have interaction. So this is a constant. The internal energy is a constant. Now the only term is T times S, and I have S here. S is here. And this consists of 2 parts. One depends on the volume, and another one depends on my arbitrary constant. But although it depends on A, the absolute value of everything depends on A, it's only an offset. So the volume dependence does not depend on which A I choose. It's not always like this. Essentially, it's always good to choose A in an optimal way. And we will discuss 10 minutes later what is the optimal way. But let's consider this example. So I have this F. F is something which does not depend on volume, depends on the temperature, but it doesn't matter. And something which does depend on volume. Now I'm looking at the pressure, and pressure is minus dF over dV. This we already repeated. I take minus dF over dV. V is only here in the logarithm. The log x over dx is 1 over x, and this is what I obtain. And this is the thermal equation of state of the ideal gas. Now we get it. And what is important, that if we do everything correctly, our arbitrary subdivision, the size of the cell A, does not appear here. It will appear there when we are considering polymers, for example. And therefore, tomorrow we will discuss how to get this A optimally, because there it's a real property. But while the real properties really appear, the things we are taking arbitrary never appear in the final expressions. And here you see how this coarse graining works. Now, what is interesting here is the following. So first, of course, I repeat it here, I didn't explain why it worked. I didn't explain how does this KBT ln S ln W comes. But we see that if we accept is as a postulate, as a proposition, it does work. Now, the most interesting thing about this force or about a class of forces like the pressure in the ideal gas is that they fully rely or they fully appear from this term in the free energy, from the entropy. And therefore, they are called entropic forces. Most forces in polymer physics, like the rubber elasticity, tangent force of polymer molecules, and so on, are at least at small elongations of the entropic nature. If you pull too hard, or if you extend too far a polymer system, then you will see the forces due to change of the internal energy. They are already connected with deformation, with strong deformation of chemical bonding, with change in chemical bonds. But at small elongations, practically all forces are, if you look at single polymeric molecules or simple polymeric materials like rubber, are of entropic nature or can be approximated as forces of entropic nature. Now, let us consider some other things, namely the model which we will use afterwards continuously as an approximation, and this is the so-called lattice gas model. Before we consider lattice gas model, we will consider something else, and you will first play a little bit yourself with a kind of very simple exercises, and we will discuss them. But first I will define the model. And the model is as follows. And now here we will need the correct optimal A. But again, it will be, everything will be expressed via, at the end, via relatively simple thermodynamical parameters. Now, I want to model a situation in which my molecules, in the ideal gas, they were point particles, and they could essentially fly not feeling that other molecules are there. But let us consider a situation again as a model, which seems as more realistic. For example, what happens if you have the molecules like the noble gases? And the molecules of noble gases are or can be relatively well represented as hard spheres. So they are balls, like the billiard balls. And there is an excluded volume. So the two molecules cannot come closer to each other, and if this is, the diameter is A, they, or 2A, they cannot come closer to each other than at this diameter 2A. Okay, A, I will say. They cannot come closer to each other than at the diameter. Now, the whole problem of packing of spheres is complicated. But let's imagine that we can, to some extent or with some accuracy, approximate this situation with a noble gas as a lattice model. And this is what we will always do for obtaining semi-quantitative approximations. So the exact numbers, the prefactors, might differ a bit. But the main dependencies, which are given by the simple lattice models, are quite realistic. And this is what we will use. This we know essentially from comparison of lattice modeling and numerical simulation, for example, of such a system. But for hard spheres, there exists a mathematical theory. If it's a little bit more complicated, there is no mathematical theory, and there you will have to simulate. So we will simply say that a molecule, we discretize the positions here. And there is only one possible molecule per cell. So the two molecules never can occupy the same cell in your system. And this is a lattice gas model. Formulating this statistically, I simply say that in a system of volume V with cells of the size A, which in reality is of the order of a size of a single molecule, or single atom here, there are n cells occupied by molecules. I can call them black. And m minus n cells with m equal to v divided by a cubed, which are empty. And now I need to calculate the number of different configurations of this system, which means the total number of ways by which I can place n objects on the total m cells, where a cell can never be occupied by two or more objects. So a cell is always empty or single occupied. And now let us discuss the following. I stop here the lecture, and I hope everybody has a paper and a pen. And let us first think a little bit about the following problem. How many ways are there? Imagine you have m Earths. It doesn't matter that it's a lattice, I have m cups. And now imagine at the beginning that I have n balls, billiard balls, and they lay here and they are all numbered. How many ways are there to place first these numbered balls in my cells? For example, how many ways are there to place 3 balls numbered by 1, 2, 3 in 5 cells? Now you calculate this and I smoke. And then we discuss. I give you 10 minutes. I take my clock, my watch. Where is my watch? I used to wear a watch. A hint is very simple. Start by placing ball number 1. And then the one who is ready switches on his or her microphone and tells us how one can get the result. I see some bored faces here. Do you know the answer?
I think so.
Okay. Tell us.
Well, what I've got is n factorial over n factorial over n minus n factorial.
So what do you propose? Huh?
So if we have one ball and 5 cells,
Yes.
there's 5 ways of putting it in.
Correct.
And if we have sorry, what I can't remember what numbers we're supposed to be using.
I didn't get it.
I can't remember what number of cells we're supposed to be using afterwards, or how many balls, or what the example questions were. But if we have 3 balls, 3 balls and 5 cells. Sorry, I didn't actually work it out.
Okay. You don't have to calculate, you can also say it with factorials.
Yeah.
So it's 5 factorial and what else?
Over 3 factorial times 2 factorial.
This is wrong. This is a result for the case when the balls are not numbered. There is always a difference between numbered and non-numbered objects. Never forget it. And in thermodynamics, it plays a role, for example, in the Gibbs paradox. It's a huge difference whether you mix the 2 portions of the same gas or the 2 portions of different gases. This is called the Gibbs paradox. But let us, okay, let us look at what happens in our concentration first with numbered objects. And then we go to the non-numbered objects. If the objects are numbered, what you have is the following. You take the object, you take first. Let's imagine we take object number 1 first. For this one, we have m possibilities to place it. I can place ball number 1 in the first, second, third, fourth, fifth urn. So I have m possibilities to place it. Whenever I have placed it, for example here, I have only 4 urns free for the object number 2. And this means that the object number 2 can be placed by m-1 ways. For example, I can place it here. This is one of the possible configurations. Now these two are away, and the object number 3 can be placed in one of the urns which are still there, which are still open. m-2. And then it's clear how it goes. It goes to m-n at the end. m-n essentially plus 1. So if I have 3 objects, I stop at 2. If I have 4 objects, I stop at 3. There are on the total exactly as many multipliers as I have the objects. And this guy now I can put down as m-1, m minus whatever, m-n plus 1, and then I go on m-n up to 1, and I divide it by m-n up to 1. So what I get is m factorial m minus n factorial. I hope you know what a factorial is. And this is the number of different placements of distinguishable objects, because I can always mark the objects. Now, let's come back to what you were speaking about, and you were speaking about the binomial coefficients, which are the placement of non-distinguishable objects. And now let's look at what happens when the objects are non-distinguishable. This is like playing lotto, where you put a cross in a cell, and crosses are considered as non-distinguishable. You don't know what cross was put for, what put first, and what was put last. So now, for each of this configuration, for example, for this configuration, let me remove this up to here. I cannot distinguish this configuration and the configuration with exchanged occupied cells. These two are now considered equivalent. They were two, but I consider them as a single. This simply means that if I have n occupied places, I have to consider all possibilities to occupy n by n as equivalent. So now I have n urns, which are my occupied places. For example, 3 urns and 3 balls. And I have different configurations. 1, 2, 3. 1, 3, 2. 2, 3, 1. And so on and so forth. So, the first one can be occupied. The first ball can occupy all 3, the second 2, the last 1, and the total number of these configurations I consider now as indistinguishable is again given by this formula, but now n is equal to n. This 0 factorial, it's 1. There is only one way to play nothing but no place. So this is n factorial. And now, if I consider objects as indistinguishable, or if they are indistinguishable, you cannot mark an atom. Quantum mechanically, they are all the same. You have n factorial such possibilities, and you have to divide these distinguishable possibilities by n factorial. And this is the binomial coefficient. I have forgotten whether you write choose where you write n and where you write n. Choose n m over n. Choose n of m. I have to have a look what is the standard way of placement, the indices by binomial coefficient. And this is what you were speaking about. So first, it plays a role for the number of configurations whether objects are distinguishable or not. It has to be defined. And if you have indeed atoms or molecules of the same sort, they are not distinguishable. Okay. There are many other funny things you have to have in mind when you are doing something like this. Just tell me how many 4-digit numbers are there? This is a question, you have 10 minutes. How many 4-digit numbers are there on the total?
$9,000.
9,000. Okay, good. Now another question. Let's say we have 10-digit numbers. What percentage of these 10-digit numbers, approximately, does not contain a digit 9 at all? So what percentages of 10-digit numbers does not contain 9?
So it's supposed to be 8 multiplied 9 square of 9. Yeah.
Just put it down and tell me up to the order of magnitude what percentage. It's 10%, 30%, 100%. I love you calculating because I'm smoking. And we will meet very similar questions when we will be doing polymers in confined geometries or things like this.
Could you please repeat your question? You mean how much?
I have 10-digit numbers. 3, 4, 5, 6, 7, 9, 10. How many of them are there?
I mean, in total, like 9 plus 10 square of 9.
$9 billion, yes. Does everybody understand this 9 at the beginning?
Because you are removing one number.
I wait for an answer. Yes or no?
No.
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 No. Why don't you ask immediately?
I'm actually, I would like to know the answer of the first question as well, like when we have 5
Yes.
cells and 3 balls.
If you have 5, first let's do this and then another. So first I tell you what this 9 is. A question is 0, 9, 2, 3, 4, whatever. Is this a 10-digit number?
No, it's a.
No, it is not. All digits are fry except for the first one. The first one is very different. There are essentially very important observations and mathematical theorems which concern the fact that the first digit of the number has different properties from the rest. So a number cannot start from 0. All the other can take 10 values, 0, 1, 2, 3 to 9, and the first one can take only 9 values. Otherwise, they are free. So it's 9 times 10 to the power of 9. This is the rest, and this is the first one. And now let's calculate. And I'm interested in what percentage of these 10-digit numbers does not contain digit 9 at all.
Is it 34%? Almost.
Maybe. So what is this?
This should be 8.
Yes.
Then the others are 9.
9 to the power of 9 divided by 9, 10 to the power of 9.
It is 34.43%.
Yes? Okay. And the longer the number, which is interesting, the smaller is the percentage of numbers which do not contain some digit. Because it is essentially, look, it's 8 ninths, 9 tenths to the power of n minus 1, where n is the number of digits. And when n goes to infinity, gets very large, this power gets very small. A large power of something which is smaller than unity goes to 0. Gets very improbable. Now about the ergs. If you have 3 or 5, then it will be 5 factorial divided by 3 factorial, which is 5, 4, 3, 2, 1, divided by 3, 2, 1, 20.
Thank you. Yeah.
You're welcome. So it's there is something to think about here. It's combinatorics. There is interesting mathematics behind, but since we will not really need it, let's stop where we are. But what we will really need is this example with the lattice guess. And therefore, let me share my screen again and let's discuss this. So here I discuss what we already discussed. This is the number of sortings of distinguishable objects. And this is this binomial coefficient, which is the number of sorting of indistinguishable objects. If we are interested only in the equation of state, in the thermal equation of state of our model of gas, it doesn't essentially play a role because this n, the number of molecules, is constant. But if we are calculating the chemical potential, it does play a role. Okay, so here I consider the distinguishable model. No, I consider the indistinguishable already. Here I consider this W. And I take the logarithm of it to get the entropy. And now I have this Kb ln m factorial, and my m was V divided by the size of the molecule cube, minus ln n factorial ln m minus n factorial. Now, already at this stage, we see why, for the thermal equation of state, the distinguishability or non-distinguishability doesn't play a role. It doesn't play a role because n, the number of molecules, is fixed. And therefore, this guy goes into a constant. While this and this do depend on the volume. And they give us a contribution to the equation of state. And now, let me do the following. Factorials are essentially very rapidly growing functions of the corresponding numbers. They are growing super exponentially, faster than the exponential of the corresponding number. But I need the logarithms of them. And to get the entropies, I essentially only need the behavior in the leading order, the number of molecules in the gas, the number of cells here in which I subdivide my system, which has to be larger than the number of molecules, is also large. So I need some approximation. I can live very well with some approximation for these factorials. And first, I propose to use the lowest order approximation. And this is a very simple one. So let me consider the logarithm of a factorial. The logarithm of the factorial is log n factorial is log 1 plus log 2 plus up to log n. Is this clear? It's the application of the formula for the logarithm of a product to this multiple product which builds a factorial. So I have here the log of factorial, the log of n factorial is such a sum. And what I do now, I approximate this sum by an integral. I say that this is approximately a sum from 1 to n, ln n the n. So what I do is the approximation which is inverse to a typical approximation of the integral by its Riemannian sum. This is an important trick. Sums are hard to work with. Integrals are simple to work with because there are huge tables for them. And there are methods of calculations. Sums are tricky. There are also methods of calculations of them. They are so-called generating functions, but one normally even does not teach this in analysis. This is so-called, I would say, the high art or the high pilotage of elementary mathematics. While calculating the integrals, you know, in your introductory course of analysis or mathematics for engineers or chemists, you definitely learned how to calculate integrals. Did you? Yes. Do you understand the approximation? No. Aha. Why didn't you ask about this? So, okay.
I assumed you were going to talk about it.
Do I have to explain?
That will be nice.
Do you remember what an integral is?
Yes. I don't understand how the sum approximates the integral, but yeah, it would be nice.
I will explain you how physicists understand mathematics. When you were considering, so imagine you have a function on the interval from A to B.
Professor, can you please adjust the camera?
Yeah, I will show it to you. Just a second. And I will concentrate on myself. So I have a function from A to B. The integral is essentially an area below the graph of the function. This you know. How do I calculate the integral numerically? I can, for example, use the method of rectangles. Yes? Here, do this by rectangles. And I say integral from A to B f of x, the x is approximately 1 over h sum f e from 1 to n f from xi, so xi times h, because f on xi, I separate, I divide my interval by the node points xi. The distance between the two nodal points is h. This is the step of integration. And then I say that this integral is approximately the sum of the areas of these rectangles, which is f of xi times h. And this is called the Riemann sum. And then officially what I do, n is here b minus a divided by h is the total number of the nodal points. And then mathematically I say it's limit n goes to infinity, or if you want limit h goes to 0 of this integral sum or Riemannian sum for the corresponding interval. Did you have this in your introductory analysis of calculus? Did you? Possibly
a long time ago.
But this is a definition essentially as a limit of the definite integral. Now, if you are calculating integrals numerically, you use, of course, better formulas than the rectangle, but essentially you are not doing something very different. The only thing is you take h small enough and you don't take a limit. And this is an approximation. So essentially the definite integral is defined as a limit of the sum. And now what happens if I don't take a limit? Then I have the integral approximated by the sum, or the sum approximated by the integral, depending on from what side I look, from the left or from the right. And now this is exactly the approximation I do now. So what I do, I have here a sum, and I approximate it with the integral with step 1. So this sum is the Riemann sum with step 1, with h taken to be unity. Whether it's close to the limit or far from the limit is a different thing. But essentially, I can, because many people did it, starting from Cauchy, I can even tell you what the error is. But now I don't want to, because I want somewhere else. But one can also approximate the error. of such an approximation. And the integrals are nice because they are easier to calculate analytically. So I approximate this sum, which is log of factorial, by this integral, because I say this sum is the Riemann integral sum for this integral if I take h equal to unity. Whether the error is large or small, this is a different thing. Here it will be not very small, but I can also get a better approximation. So now I can calculate this integral. Now, is this part understood? Yes. Okay, wonderful. So I can calculate this integral, or I can look up the integral in the table of integrals. I know what the indefinite integral is, and then I have to put here the limit. You know how to calculate the definite integrals. You look up in a table an indefinite integral, and then you take the corresponding stem function at the upper limit, and you subtract the stem function at the lower limit. So, and this is what I get. You can check that this is the integral by direct differentiation. If I take a derivative of this guy in x, I get exactly ln x. I hope I don't have to show how to take a derivative. If you want, I can show how to take a derivative. And this is my approximation for the sum. So what I see here is that log n factorial grows as n ln n minus n plus 1. This is a very rough approximation. It's not a very nice approximation, but it's enough for what I need, because I know that the entropy is additive. It's an extensive variable. It has to grow as n, as the number of particles. Here I have, and the entropy, there comes this, it's exactly the log of this guy minus log of this guy. So I have to keep this term and this term. And I don't need anything which grows with n slower than n. This guy grows with n faster than n. I have to keep it. I will see how something which is additive appears from it, but by itself, before I subtract, it grows with n faster than n, because this grows as n, as this also grows. Ln n is a slowly varying function, so it's practically additive, but I have to keep these two terms, and this I can negate. Here I have a better approximation, and this is the so-called Stirling formula. This is what happens if you take the higher approximation. It starts from a different integral representation. It's not as rough as simply saying that this guy is approximately a Riemann sum. Again, I don't want now to give a lecture in mathematics, in the theory of approximations and in special functions, but if you do it better, you obtain this. So what do you get here? You get this term, n ln n, it's here. You get this minus n, it's here. Instead of 1, you get another constant, ln square root of 2 pi, which is essentially practically 1. But what you get, which might be important, it will not be important here, but it is important in the case, in the situation we will consider next week, we get half ln n. It's a slowly varying function. It's almost a constant. Logarithm is almost a constant, but still it's growing with it. And this is the Stirling formula. It's really a fruit of genius. It's really a mathematical wonder, because it is, these are the first terms of so-called asymptotic series. It's essentially a diverging series of which the first terms give a very good approximation. And I will show next week, I don't want to distract us, to distract from the main line of discussion now. I will show how small the relative errors here are. You can also calculate them yourself. If you use this approximation, it's approximately, I will change the sign. ln is approximately this guy. And then, you know, it has an accuracy of around 10% for n equal to 2. And for n equal to 10, it has a relative accuracy of around 2%. And then the accuracy grows relatively fast. So the factorials grow very fast, but the relative accuracy of the Stirling approximation also grows fast enough with the value of factorials. The larger n, the smaller is the error you do. You practically can consider, for whatever practical situation, you can consider this as exact. Learn it, it helps. We will use it continuously during the first 4 or 5 lectures. Okay. Now, since I'm only looking for additive contributions, for contributions which are growing as n and maybe faster, for me, our first formula is enough, our simple one, which we got from the Riemann sum. So now I can put here my simple approximation for these factorials. So this is m ln m minus m plus 1 if you want, but I have already forgotten 1 because it's not additive. And then I have n ln n plus n. And then I have m minus n ln m minus n plus m minus n. And the first thing I see here is that all the linear terms cancel. So this is what I get. And now I use it in my thermal approximation, where I simply say, okay, this U, the internal energy, it's there, it's temperature depending, but it's a constant. And if I'm looking for the equation of state, it doesn't play any role because it's not dependent from the volume. So therefore I simply omitted it here. And now I remember and remind you that m is volume divided by the size of the cell, which we put to be approximately equal to the size of the molecule. And we calculate the free energy as a function of the volume by putting everything what we need there. And now what we get at the end, I will show it to you because it said is now left for tutorial. But okay, let me give you 10 or if you want 15 minutes to do the following exercise. Start with this expression. I will leave the expression there. Put first n equal to phi times m, and phi is the volume occupation fraction. It's the fraction of the volume of my lattice which is occupied by the molecules. Let me come back just a second. Stop. Let me come back to my initial figure. And then we will discuss. For this, I have even put down the full solution. Again, I think that there was a mistake there, but I will correct it maybe tomorrow. This is This is my lattice model for the lattice gas. See? Now I have on the total M equal to V divided by A cube cells. N cells are occupied by molecules. And each molecule has a volume of a molecule is A cube. Now phi is the total volume of the molecules is N A cube. This is called excluded volume because it's not free. There the molecules cannot move. It's the volume which is occupied. So phi is either N over M or N A cube divided by V. It's the same. This is the volume fraction of the molecule, and the rest is 1 minus phi. So what I propose you to do is now the following. Just think and then we will discuss. Now I come back to this formula. Start here, multiply it with T, so start here, and then obtain this formula, first via phi, then express phi via V, and obtain the pressure of this lattice gas. It's quite a reasonable approximation for the pressure for the equation of state of the for the noble gases, and then we will discuss this approximation. If they will be complicated to differentiate, stop there. Now you have, let's say, 10 minutes, and then we will discuss the solution. And I will put then a solution online because we will repeatedly use it as a reference when we will consider more complicated situations with excluded volumes. So now it's okay, it's past, almost. You have 10 minutes, and then I will show you the solution. Work and smoke. If you want to talk to me, just switch on your micro. I am here at another computer. Essentially, I have 2 more computers in my office and 2 more screens.
Professor?
Yeah, I'm here, I'm coming.
Yeah.
Okay, here I am.
Yeah. I have a question about the we talk about the 3 balls in 5 places.
Yes.
Yeah, I mean, after thinking, I think it should be 60, not the 20. It's supposed like we pick up 3 places from the 5 places, so it should be say 5, 3, and multiply. We have to arrange the 3 balls, so we should like multiply 8, 3, 3. So it should be 10 multiply 6 should be 60.
Once again, you
Yeah.
can place the first ball at 5 places, the second at 4. Yes, you are right. It's 60.
Okay.
And the last one at 3.
Yeah, so it
I
should
divided wrongly. Yes, you are right.
Okay.
Do you want to play with lattice gas a little bit more, or we can discuss, so to say, the rest of solution? What do you propose?
Both okay for me. I don't have preference.
Other our students? So you can play 5 more minutes and then I show the solution, or you can have the solution immediately and then we discuss it and stop for today. And I will put the solution online probably tomorrow because quarter an hour after finishing now, I have another meeting. And tomorrow in the evening, I will be free because I have another lecture before your lecture. So what do you prefer?
My preference is that maybe we can discuss the solution right now.
Okay, good. Let's discuss the solution right now because I have it here. Let us guess. I am not sure. I used here a different notation. And essentially, we don't need all these corrections. So maybe I will have to rewrite it. My former M is here N, and my former N is now small n. But I can improve it before I put it online. I will do it tomorrow. Tak, LN. And now tutorial, a second, because I simply took something I have written last year And I have, of course, didn't have a look. Tutorial, let us guess. A second. Yes, modify notation. I will rewrite it, and I don't need now the full Stirling formula. Whether I use all these 1/2 or not use these 1/2, it doesn't matter. So the first thing I do, you can forget these 1/2, but you can also keep them. The first thing I do, look, I put out all these m's. So what I do is to write n as phi m. In my new notation, this is m. So now the number of cells is capital N and number of molecules is small n. I can modify it if you want. So now I'm going here with the Stirling formula, and I obtain these plus corrections. So you see that the corrections which one obtains if one uses the full Stirling formula are sublinear. And if I come back to the lecture, you see that I switched.
Actually, I couldn't see anything.
You can see, why don't you say that you can't see anything?
Because I thought that you are just saying that I will do the correction and then upload it. So I
just a second.
Actually, everybody's like not seeing anything.
Just a second. Now, this simply means that I have to repeat sharing the screen. Just a second. Where I am? I am not here. It indeed has lost the. Just a second. This is something different. I close this. I close this. Close all. Now let me start with lecture. Stop. Mm-hmm. No. Okay. Here I am. 1. Here I am 2. And now I share screen with you once more. I'm here in Zoom. Share screen. Do I have it? I have it. So this is my tutorial. This is my lecture. So here in the tutorial last year, I started from the full Stirling formula and used it for the factorials. But at the end, up to the small corrections, I arrived at the same expression which I gave you in the lecture. It's here. If we go to the end of the lecture, you see this. And the only thing here was that I have lost the minus. No, it's without minus. So this and the one in tutorial, I will rewrite the tutorial for you. They are essentially identical. And then if you get into the free energy, you have here minus ST, so you get plus KBTN and so on. So this is the expression. And now you can do different things. First, you can, here I am expanding. First, you can simply put instead of the phi, what you have to put there, namely, if you look at my blackboard, phi is NA cubed divided by V. And then you can differentiate it with respect to V. Or you can expand this guy in the Taylor series. Because phi is smaller than unity, you can easily expand the logarithm. This guy you can hardly expand, but 1 minus phi is easily expandable. And you get here the Taylor series, and then you can differentiate. And what you obtain then is the expansion of the entropy and of the free energy, and then of its derivative of the pressure with respect to the volume. And this is called the virial expansion. And this gives you the equation of state for the non-ideal gas, for this lattice gas, or for a lattice model for a noble gas as a function of volume. Now, what I'm doing here, you know, I will rewrite it. I will modify the notation to match exactly to the lecture. So what you can do, you can introduce the concentrations, the number of molecules per unit volume, and express P of V as a function of concentration. The first term is the ideal gas, and then you have the corrections to the ideal gas. And this expansion is called the virial expansion. These are the virial coefficients. And then there is an interesting thing there. And this interesting thing there is that it's very general, it's a very general statement that the entropy, and then therefore the free energy, and then therefore the pressure of a system with interaction, because introducing the excluded volume, we introduce the interaction between the particle. The expansion of the entropy or whatever other thermodynamical parameter of your system with respect to volume starts from the ideal system here, the ideal gas, and then it has the terms which are power laws in concentration. This is a universal behavior, and we will use this universal property, for example, when considering also the polymers, where we will say we start from an ideal chain as an ideal system and then look at the corrections. Because we didn't show it, but this kind of expansions essentially work universally, and I wanted to show it here just on the simplest example. Now, you know, what I will do will be to modify it and to make exactly the same notation as in the lecture. I will also do another thing. I will put down here the full expression, and then maybe tomorrow or maybe next week, we will shortly go through it once again, because this is not for nothing that I have written it. I will refer to it at least twice more during the course, because we will see very similar expressions for binary mixtures and for polymer mixtures, for polymer solutions and for polymer blends. So therefore, this is an important thing to go through. Now we don't have time, so let me change it a little bit, and we will return to it maybe tomorrow. So now let me close the screen. I think that maybe you have heard a bit more than you can digest during one evening. My excuse is that most of things I was talking about today you had to have learned during your thermodynamics courses, whether they were in chemistry or in physics. And what can I do? We only have less than 2 months, you know. Okay, so ladies and gentlemen, see you tomorrow. I close it for today. And we meet tomorrow at 1. Today I will not make changes because I will not have time until late in the evening, but tomorrow I will correct the mistakes I have seen and harmonize the notation between my tutorial and the lecture, and then I will put tutorial online for you. With this latest guess.
Thank you very much.
Okay. See you. Bye.
Thank you.
Thank you.
Thank you.
Thank you.
Bye.
Bye.
Bye. And I leave the lecture for now.